Thank you. Good morning. My name is Zeydy Ortiz, and this is Rob Montalvo. We are Data Crunch Lab. We help teams and organizations with their technology solutions and their data analytics. We love to support the local data science community, and PyData Carolinas is part of the work that we do with the community. So we have been part of the board of organizers. On behalf of the board of organizers and ourselves, we welcome you to PyData Carolinas. So this morning, we are going to be talking about scalable data science with Spark and R. If you try to install SparkR, don't worry about it. We will work in a hosted environment. Earlier, we showed the information about Databricks, but we'll show that again at the appropriate moment. The intended audience for this tutorial are people that are familiar with R, people that are familiar with machine learning concepts, but they may be new to SparkR. If you are not familiar with R or machine learning or know a lot about Spark, talk to your neighbor and help each other out, and hopefully, and we hope that you can follow along. So the objectives for our tutorial today, Rob is going to give us a brief overview of the basic concepts of Spark. Then we're going to go into the Databricks environment to learn how to explore data in SparkR, perform interactive analysis, and hopefully we'll have enough time to run machine learning algorithms in SparkR. So Rob?
Thank you, Zeydy, and good morning, everyone. I hope everyone is as excited as we are to share our knowledge of the technology, and that we also hope that this is going to be an informative session for you and that you take the most benefit from the experience. As Zeydy alluded to a second ago, my contribution, my main two objectives that I'd like to accomplish with my part of the presentation is to, number one, to provide a very brief overview, high-level conceptual overview of Spark, and most important, pave the way for your interaction with the notebook you will be using with the tutorial. That said, only if it works. Got it. So Spark is a general-purpose cluster computing system that provides support for fault tolerance, which means that if a node in the cluster goes down or a node is acting too slow, another node from the cluster will pick up the slack and effectively restore the performance and the functionality to the system as a whole. The complexity associated with maintaining this fault tolerance is hidden from the programmers behind the APIs and the runtime. Spark also partitions big data across multiple nodes in a cluster and stores the data, and this is very important to notice, on the memory in these nodes. And you will see later why this storing data in memory is actually very important and very critical. So Spark offers targeted support for certain use cases, such as structured data and relational queries via Spark SQL. It provides support for processing of real-time streams via Spark Streaming. It also has a built-in library for machine learning, and it supports graph processing via the GraphX API. So at this point in time, some of you might be wondering, why Spark? Well, the short answer is that Spark is actually very fast. And there's reasons why Spark achieves such speed. And one of them has to do with the fact that it supports massively parallel computation, which implies coordinated execution of code by multiple processors that work in different parts of the program, with each processor using its own OS and memory. As I said earlier, one of the main salient features of Spark is that it keeps data in memory. Some of you may be familiar with Hadoop. Hadoop also has a similar concept, except that the data is kept in memory and sometimes spilled into the hard drive, and there's a cycle usually that goes from hard drive to memory, and that I/O bottleneck presents performance issues for Hadoop. This is strongly minimized by Spark keeping things in memory. Another feature that makes Spark fast is that Spark is also partitioning aware, which means that it knows where to keep the data and what nodes to keep the data close to. In other words, trying to avoid shuffling data over the network, and therefore it reduces the impact of network latencies. If you are interested in writing an application for Spark or using Spark, there's support for writing an application using Scala, Java, Python, and R. And if you know SQL, you will, some of the constructs that are provided by Spark are going to be very familiar to you. One important concept that I wanted to highlight is the fact that a Spark application consists of essentially two programs, a driver and executor or executors. And the driver, you can think of it as a main or the main loop that executes the code, and it runs on one machine. And the executor usually runs on machines in the cluster, and that's how it achieves the parallel execution of code. One concept that I wanted to bring to your attention is the RDDs. You might have heard of resilient distributed datasets, and it is the main abstraction that Spark utilizes for elements that are partitioned across nodes in a cluster for parallel processing. With Spark 2.0, which is the support we will be using today with Zeydy's tutorial, they changed the nomenclature to be SparkR DataFrame as opposed to DataFrame. It's still the same concept, and it is essentially a distributed collection of data into named columns, conceptually similar to a table in a relational database. Some interesting and important properties that SparkR DataFrames have are that number one, SparkR DataFrame is immutable. In other words, once it is created, it cannot be changed. So as you will see throughout the code, there will be multiple interaction operations against data frames. That implies that you start with a data frame, the operation or the transformation changes that data frame into a new data frame, and that essentially translates into data frames being created on the fly in response to an action, but we'll get to that a little bit later. Another property is that data and SparkR DataFrames are distributed across all the executors in a cluster. They can be created from many different sources, Hadoop file system, text files, JSON, Parquet Hive, etc. Data frames can be cached in memory for later use, so if your application, throughout your application, you may want to deliberately request that a SparkR DataFrame be cached, because by default, once the data frame is used, it basically gets destroyed once it's no longer needed. Data frame must have a schema, which implies that they have to have a name associated with each column and a type for each one of the elements in that column. As I alluded to earlier, operations in Spark can be classified into either transformations or actions. Transformations are lazily evaluated. What that means is that they're not executed immediately when the call is made, but rather an interaction happens with other backend components that effectively create an execution plan. Only when an action is triggered, and that's the other type of operation, only when an action is explicitly requested, the transformation code is actually executed. And obviously, we create a new SparkR DataFrame from an existing one. The actions, as I mentioned earlier, is the main mechanism for Spark to get results. and it is what triggers the execution of the transformations. So at this point in time, we're getting to the point where I will be very close to handing it over to Zeydy for the main part of the presentation, the most important one. I'd like to bring to your attention that we are using a hosted environment called Databricks. I know that some of you approached us at the very beginning and told us that you had run into problems with setting Spark up. This may be beneficial for those of you, for everyone, but really for those of you who had problems with that. This will be a lot easier, or should be a lot more straightforward and less hassles. So these are the instructions. By show of hands, is anyone here in need of help with setting up the Databricks account, or has any issues after having tried to do so? By the way, we have Danny here to help. Danny is very familiar with Databricks, and he will definitely be able to assist if you run into any issues. Another thing that I wanted to highlight is that Databricks specifically states that they only support Google Chrome. So those of you who are in Apple or are in Windows and are using Internet Explorer, you may run into issues. They claim it is unsupported. You may get it to work somehow. However, if you are running into any limitations, please let us know. You may want to switch to Google Chrome or partner up with someone that is running Google Chrome near you.
Are we ready to proceed? Everybody has an account. Okay, so let's go through that. Anyone else has any issues with getting into Databricks?
Can you go back a slide for a second?
Yes.
Are the slides posted somewhere?
Sorry?
Are the slides posted somewhere?
Not yet.
They will be. Along with the notebook, by the way. So if you run into any issues, the notebook will be published, and you will have access to it along with our contact information. So if you run into any issues, feel free to try things on your own and contact us. Let us know if we can help in any way. So without any further ado.
If you have the ability, put that into another browser window because we're going to grab that long URL.
Take it over. So I'm going to transfer it over to Zeydy, and thank you very much for coming, and I hope you have a great rest of the day.
Okay, so hopefully everybody is inside of Databricks already, and they have the bit.ly open in another window, because now you need to grab that URL. It's a very long URL, and work in your Databricks account. Let me switch back to Databricks. Okay. So you may be in this view where this is the home view. Oh, you cannot see my window. Just a sec. No. Let me try. I need to escape. Okay. So now we're in Databricks. I press the home view. You may see the workspace users and your username. And that's where you will see the pop-up. Go to import, where it says import item, the URL. You cannot enter the bit.ly URL there because it will not resolve. You need to grab the long URL that you had from the bit.ly before in here. Let me try that. Okay, and then press import to get to the to what you need. I don't want to do that. Okay, anyone needs help getting to importing their notebook? No, okay, perfect. So to run this tutorial, we need to create a cluster, and we're going to do it over here. At the top, you may see detached. If you are detached, then click on that logo, and it will ask you to, I'm gonna be brave and detach. Did it work? Terminate it. I was brave. So you may be asked to create a new cluster. Let's see. Create a cluster. You give it a name. Now make sure that the Apache Spark version is 2.0 Scala 211. It's probably at the end of your system. Some of the code that we have in there are specific to Spark 2.0. Then you will create your cluster and wait. Okay, at this point, anyone needs help attaching to their cluster? Mine seems to be deploying. Aha. Perfect. Anyone else needs help attaching to their clusters? Okay, we need help over here. So we seem to be having Wi-Fi issues. Sorry? So while we wait for everybody to attach, one of the main things that I want to put a picture in your head about SparkR is the idea that we have a driver program and worker nodes. R and SparkR live in the driver area, in the driver program. Everything else is part of Spark. So to be able to access the data that is in the executor nodes, we have to communicate and do the APIs. So we're going to be looking at how we're going to bring data back and forth from the R to Spark and what to do and not to do about that kind of data. We still need some more help. So this notebook is already an R notebook. When you do it for the first time, yes, you have to create the language. You have to select what language you're going to be using. Yes, so that's when you are trying to do a new notebook, and I will try to do this. That this is where you create a new notebook and you put a name and you select the language that you want. Yeah. But this notebook that we had already created is already in R, and we can see it at the top. This is the name that I selected, SparkR tutorial, and in the parentheses it says R to indicate that that's what is running. Okay, so as we indicated before, our objectives are to understand the basic concepts of Spark. We're going to be doing data exploration, performing interactive analysis, and running machine learning algorithms. As I mentioned, we need to make sure that you're attached to a cluster running Spark 2.0 and Scala to 11. To navigate between the cells in Databricks, you can use Control and Enter, and that runs the code in the cells. Now, if you use SparkR in another environment, this is a hosted environment, and they are already putting together the context and doing all of the configuration for us. We don't need to do that. But if you're running SparkR in your own environment or hosted in another platform, you may have to do library SparkR and then start the session. In Spark 2.0 is called SparkR session, but in previous versions of SparkR, it was SparkR init. So make sure that depending on where you're trying to run this, you know what command to use to get started. Anyone, everybody attached? No one else having issues? So we still have one more issue. 2, 3. And to make sure that you're attached, you can run the first command, SQL context, and it will give you an ID. So I have annotated the cells with some of my comments, but also I've tried to bring in some of the manual page descriptions for some of the SparkR commands. So if you run this at home, you will be able to have that as a reference. Okay, we are going to proceed with the tutorial, and if you would like to work with your neighbor or follow along as we move. So the second command that we're going to run is the SparkR conf. That tells us what the configuration for our session is. It gives us a lot of information, but the one that I wanted to look at is, let me check what's the name. The Spark driver max result size. So if you scroll down on the window to find that, Spark driver max result size is 4 gig. What they have done is when they configure the driver node, what they are telling the executors is, do not send me more than 4 gig or my driver would run out of memory, and that wouldn't be a good thing. So that is a configuration in there, but something to keep in mind when you're writing your code.
Max reserve size, is that referring to the input file or the output file?
It refers to the data that the executors send back to the driver node. Okay, so let's get started with the exploration of the data. We're going to be looking at the differences between executing a command in R and in Spark. Okay. I'm going to give you an overview, but if you are still having issues, let us know and we can try to help you with that. So we're going to learn in this particular part how to bring data into SparkR and how to perform some structured data processing. What we're going to be using is exploring the Old Faithful geyser data. Well, many of you have been to Yellowstone. That must be a sight to see. I've never been, but it is called Old Faithful because it is said to erupt exactly at hourly intervals. So one of our data sets is a historic data about the wait time between eruptions and how long the eruptions lasted. So we're going to be looking at that. It is not big data, and as we will see, but we will see how to get that from the R environment into the Spark environment and how to work with it out in the Spark environment. As an exercise for the reader, you're welcome to bring in big data to be able to do this with more of your data set. And I have also included links to several reference material. And one of the links is the webcam for the Old Faithful geyser. So if you are lucky to hit it just at the right time, you will see the eruption. So what are the questions that we want to be looking at? With the historical data, we're going to be looking at how long is the wait time between eruptions, how long is the duration of an eruption, and also we're going to look at what's the most common waiting time, and for that waiting time, if you had to wait that long, how long was the duration? My cluster doesn't seem to be working, but we'll try it. Yeah, maybe the Wi-Fi. Mm-hmm. Okay, looks like I got it. So if you're if you're familiar with R, if you have the question mark, that brings up the documentation, and since this is a data set that is usually in R, you will see the information. It's a small data frame with 272 observations, and the variables are eruptions and waiting. So as Rob mentioned, the Spark data frame used to be called just data frames before Spark 2.0. They have been inspired by the work done in Pandas, in Python Pandas, and in R. And they are organized into named columns. So every column has to have a name. It has to have a type. And they do optimizations on the data and under the hood. And that's something that we don't need to worry about, but it is something that they provide for the execution in Spark. So what we're going to do is bring in the faithful data set into R with the faithful _ RDF. I am naming it that way so that we know what is an R data frame versus what is a Spark data frame. And then we're going to take the faithful RDF and create a data frame in Spark. So the command here is create data frame. That is the one that brings the data into the Spark environment. We're going to cache this Spark data frame and persist it in memory, only for our benefit. But if you're going to be working with a data frame that is going to be read repeatedly and that you need for a long time, it's better to have it persisted so that if the memory fills up in the cluster, it doesn't get kicked out to other storage. Now we're going to run a few commands that we normally do when we are doing data analysis in R. And the first one is str for the structure. This is the structure of the data frame in R. So you see this is the type, data frame, and the 2 columns. Let's look at the object size. This is object size reports the space allocated of that object in R. So the data seems to be taking about 5K in the R environment. Now let's do the same for the Spark data frame. The str command, which is an R command, gives us basically the same information. It tells us the type, Spark data frame, and the name of the 2 columns. And also the type of the columns. Now, if we run object size, we see that this object in R is only 1K. Why? Because that is just the memory that is occupied in the R environment. Remember that picture where we had the R environment around the driver and the Spark around everything else. Only in R, we have some information. It's probably the metadata for the Spark data frame, so that it does not live in the R environment. It lives in the executors. We can take a look at the Spark UI, and to get there, we go View Spark UI. Gives us another window. So the Spark UI gives us the information about the cluster and about what's happening in the cluster. We're not going to be covering that part about the configuration and all the cluster, but I wanted you to see that the Spark DF is located in the in the Spark environment, if we ever get it to work. Well, this is the view that I ran earlier. And you will see that we have an RDD with eruptions and waiting, and the size in memory is 4.6 kilobytes. To get there, you need to go, I believe the view is jobs, but you need to go into storage. That's where the information, where you will find the information. And by the way, we see this in storage because we had persisted that data. If we didn't run persist, it will not show up in this view. Okay. So if you have done Spark with Python before, you may think of using show, but it does not work the same in PySpark as it works in ours. So let's see what we get. What we get is basically kind of the same information of STR, the Spark data frame, the type of the data frame, and the columns and their names and their types. So the next command that gives us basically the same information in the print schema, and it's in the true format. Now we're gonna, everyone all right? Following along? Yes. About storage. Okay, so under attached, there is a view Spark UI, and it gives you another window. The window opens under Jobs, and you will go and click on Storage. And you will see this part. Okay. Okay, so now let's view the data in the R data frame. As expected, you will get the whole listing of the data frame and the data in it. All 272 data points. Now let's try to do that with the Spark data frame. And all we get is the schema of the Spark data frame. Why? We have not run an action into that Spark data frame. To run an action, one of the actions that we will be looking at is collect. Let's do collect. And collect works, basically brings all of the data that we just asked it to collect into an R data frame. So the view is very similar to what we have seen for the R data frame, and we will see the 272 data points. But what if you're working with big data? You don't want all of the data back into your R environment, because that's where you would run out of memory, and that was not the point in the first place. So that's why you need to be very careful about using collect. You will go directly to out of memory jail, and do not pass go, and do not collect $200. So be very careful with that. Instead, we're going to learn about other commands that we can use. As expected, first we'll return the first row. Head works the same as in an R data frame, gives you the first 6, but you can also give it another number if you want 10 or 15, whatever you want. You would use show df, and it will give you a nicer table of what's the content. It will show only the first 20 rows as a default, but you can also give it another argument. And the other one is take. That one needs an argument to know how many to take. Usually we would do this to have an idea of what kind of data we have in our data frame. Now, one of the things that is unique to Databricks is they have a command called display. And if you run that, if you run that for the first time, you will see the data displayed in a table, but you can also look at the data in a different view with a plot. Down here, there's a button where you can select the type of plot and plot options. This one has the default values. It found that there are 2 data points, so it said one is X, the other is Y, but later we may be able to play with that. Okay, are we good so far? Very good. Again, so far what we have done is run an R command into a Spark data frame and see how it behaves, and how we make the command to behave the way we used to think about it. So if you do just the name of the variable, it will not give you all of the data. You have to collect it. But collect, very careful. Now let's perform some interactive analysis to start to see how we can answer some of the questions. And one of the common tasks that we would do in an R data frame is do the summary. Okay, why? The summary will give us the minimum, the maximum, the quartiles, median, the mean. Let's try that with a Spark data frame. And nothing seemed to have happened. Why? we did not collect. Well, it was a lazy execution, so we need to have an action into it. I am putting that into 2 lines so that we can see first the command and then the collect. So summary on a Spark data frame gives us similar information than what we have for an R data frame. Count, mean, the standard deviation, which is normally not for the summary in R, but the minimum and the maximum. We can also use describe, and describe is another construct that is used in Python, and it will give you the same information. So here the caveat, once again, just because you can doesn't mean that you should. Just because you can run summary, just because you can run collect, doesn't mean you should be doing that, because summary will go through all of the numerical columns. It will go and try to count them, to process and find out what they mean, the standard deviation, the minimum, and the maximum. So we have 5 different operations that we're running, 5 different statistics that we're running for all of the numerical columns. One other difference in a summary between an R data frame and a Spark data frame is summary in an R data frame will also tell you a little bit about columns that are not numerical. He will give you, if it's a character, it will tell you it's a character, and then it has 272 data points. And it may tell you how many NA values are. But for a Spark data frame, it only runs on numerical columns. Okay, so to answer our questions, instead of going through the summary, because we should not be doing that, let's calculate individually for each one of our columns what the questions that we had before. To find the average waiting time between eruptions, we want to use average or mean, and then the average duration of an eruption, also average or mean. To do that, we are going to use aggregate functions, and the syntax, the syntax is you give it the name of the new data frame, the aggregate, the name of the Spark data frame that we want, the column aggregate function, or use the alternate syntax. So let's try to calculate the average wait time between eruptions with the first syntax. Notice that waiting here is the column name, mean is the function, and I put it in quotes. The syntax is very important, and if you don't do it that way, it will give you an error, and it will be crazy at 2 o'clock in the morning. And the action that we used here was first. We just got 1 data point, but if we don't do first or we don't do anything like that, it will not give us the information. So to calculate the average duration of eruptions, we're using the alternate syntax. Notice in this case, the function is not in quotes. We are using a call to mean with the Spark data frame column, but I had to specify both the name of the data frame and the column that we're using. So it's a little different from the previous call. In the previous call, we did not have a name for the column, so Spark already assigned a name with the name of the call. But here, I had assigned a name for that result. So if we do that again, we could access the information that we had just calculated by going through result dollar and the name of the column. So this 3.48 is stored in the column. You have to go access it from that column. So that's a good reason to give the column a name. We could perform more than 1 aggregation at a time in a call. So here we're going to find the minimum and the maximum duration. And since now it is in the duration object, we can access both the minimum and the maximum later if we want to. So if you were paying attention, well, I wasn't, but the end result is that historically the wait time between eruptions was 70 minutes, and usually they last about 3.5 minutes. But now we want, and one thing to note is that we only did a calculation in one column. What if we need a calculation that relies in both one column and something else in another column? And that's where we're going to go for answering the remaining questions. To do that, we're going to use the data frame operations that include group by, select, filter, where, and arrange. And I believe most of these are already an R function. So group by creates a grouped data frame inside of Spark, and then we can run a function on that grouped data. If we do head, it has aggregated all of the waiting times and counted how many times they appeared. So 70 minutes was 4 times, 67 minutes was 1 time, etc. So let's take a quick look at that data with the Databricks display. Originally, you will see a table like this, but I had selected the bar chart down here, and it gives us a bar chart with the data, not in any kind of order. So remember that the first data point was 70 with 4, and the next one 67 with 1. We can take a quick look at it and see what are the values. Now, we had collected the data from the aggregation on waiting counts. That is an R variable. So now we can also display it with plot. And since we can influence what are the options in plot, we can have a better way to look at it, even though unfortunately it's not as interactive as the other one. But we see 78 is the most common waiting time. The other aggregate function that we're using is arrange to arrange in descending order all of the waiting counts, and then we can grab that first one with 78, because now to be able to answer the question of what are the distribution of the duration of the eruption, we need to get that 78 and find out with the filter operation. Filter will bring in the rows that are going to satisfy our condition. Our condition is that the waiting is the most common waiting time. I changed that to a box plot down here to be able to see for the most common waiting time, we have an eruption that lasts between 4 and 4.6 minutes. We're done with that data frame, so we can unpersist. So we're telling Spark, if you need the memory, go ahead, use it for something else, don't worry about it. Okay, so Old Faithful is said to be erupting every hour, but as we have found out from the historical record, it's about 70 minutes that you have to wait, and it will last around 3.5 minutes. But if you are lucky to get to the most common waiting time of 78 minutes, then the eruption will be a little longer, from between 4 and 4.6 minutes. So that's quite a show. So far we have looked at the DataFrame API. We examined the structure of both the R and the Spark data frame and learned about actions, aggregate functions, and the operations. Everybody following along? Woohoo! Okay, so now we're going to do the second part where we're going to run some machine learning algorithms. With Spark 2.0, we have an expanded ability to run machine learning in Spark. Before, we only had a generalized linear model with two families, the Gaussian and the binomial. But now with Spark 2.0, we have 4 different machine learning models: GLM, the accelerated failure time, survival regression model, naive-Bayes model, and k-means. We also have the ability to save and load the models for later use or for sharing. For this part, we're going to do the classical data set of identifying irises. There are 3 different irises in the data set, and they are the Setosa, Virginica, and versicolor. We can get information about that by running the R command !iris. And we will see that it has 150 rows and 5 different variables telling us what are the measurements of these different species. Now let me show you something that this is what the iris dataset looks like in R. It has sepal.length. I hope that's the right way to pronounce it. Sepal.width, petal.length, and petal.width, and the species. Before, we put data into Spark by having an R data frame into Spark. But how do you get it into R in the first place if it's really big data? What we need to do is, well, what we could do is to read it from a source, either from a CSV file, JSON file, or with a database, a Parquet, ORC, or with a connection to a through JDBC. There are methods to do read and to do write, so it is able to do that. And what we're going to do is, instead of reading the data from the R data set, we're going to read it from the Databricks file system just to see that it works. Now, as I mentioned before, the original data has a dot in the name of the columns. And when we run some of the algorithms, it's not going to like it. So in this case, we have to put in the schema of the data set. So I have a schema, the type, and then each of the fields. I named the first one ID, and the type is integer. Now I change sepal underscore length instead of sepal dot length, and that's a double. Same with the width, petal length, and petal width, and then the species is a string, not a character. In Spark, it will be a string. So the function that we're going to use is read.df, and it takes the path of where the file is. You have to specify that the source is a CSV, that you have a header, and specify what the schema is. And we're going to persist it too. So let's look at the schema, and it tells us the same information that we gave it, so that's a good thing. And as expected, we have the same information that we had before. So we're going to run 2 machine learning algorithms. The first one is supervised learning. In supervised learning, you have a label that you can train your data on that label to find the structure, and it will create a function that you will be able to predict what the new labels are for the data that it has not seen. So we'll use the binomial generalized linear model. We have 3 types of irises, but we're going to run it only on 2. To do that, I had subset the data into the versicolor and the Virginica to then run a sample and to get the training data, and then do except to do the testing data. and then put it all together in Spark. All of these commands are running with the data frame in Spark. I am not bringing the data into R to be able to do that. I tried to use sample by to do this, but it did not work. So some of the things have not been implemented properly. Okay. Now, if you notice, it only tells me that the command took 0.1 seconds. Don't believe it. It's only doing the execution plan. It has not done anything yet because I have not asked it to do anything yet. Now, when I run the GLM and I specify the data frame that I want, and the formula, I want to predict the species based on the measured data and use the family binomial. That's where it's going to actually do something. And it will take some time. A little longer than all the other commands. Aha, we have results. So if you're familiar with the GLM summary, it will give you the residuals. It will give you the coefficients for your model, for your function, and some information about the performance of the model. Now we created a training data set and a testing data set. Let's see what happens when we run the model on the training data set. So with the predict, we give it the model and the Spark data frame with the training data set that we had. Remember that training had the ID, the sepal length, and everything up to species. The model appended a couple of columns. One of them was the label, and the other one was the prediction. The label is the label for the species that we had before. So it looks like 0 is versicolor and 1 is virginica. Now, the prediction is these numbers over here. But to be able to find the prediction, we do the if-else so that we can properly classify between 0 and the class 0 and class 1. Okay, so now we have another column here with class, and the prediction told me that this would be class 0. Let's scroll down to look at it. Displaying on Databricks will give you up to 1,000 rows. So it is safe to use in your driver program. Aha, we have one that doesn't look like was the right one. Those are perfect. Okay, let's really see how, let's really compare the predictions by building a contingency table. Now, I am running count and group by on the Spark data frame. I am not bringing the data frame into R to be able to see what my predictions are. And then I'm doing collect because since I'm doing a contingency table, I know that it is not going to be a lot of data. It's going to be just a table. So collect is fine here. We have the predicted class with a predicted class of 1 and a label of 1, which was what the training label was. We had 24, but we have a couple of misclassified with 0, 1, and 1, 0. Now let's see how we do on a testing data set that we haven't seen before. We do the same procedure where we get the predict to find what is the new prediction with the testing data set, and then put the class label 0, 1, and build the contingency table. We had 2 that were misclassified on our testing. So for model persistence, we could write the model into our file system and then read it back if we wanted to. We're not going to be doing that. This is just a throwaway cluster, so we would not do that. But if you are interested, I have included links there for the documentation. Now, GLM binomial was already included in previous versions of Spark, so if you're running previous versions of Spark or only have access to previous versions, then you will be fine to run that. But unsupervised learning with k-means is not available. Yes? There are a lot of other commands that you can do with Spark. I am not including them here, but there are a lot of math functions that are included. I believe from Spark 1.5, they did put a lot of them in SparkR. There is a link somewhere in the tutorial for the documentation that you can take a look at that. Another question? Anyone else? It looks like we will have enough time to look at that. I put that at the end just in case we didn't have enough time, but yes, we'll look at that. And that's a new Spark 2.0 feature. Okay, so let's look at unsupervised learning. There, we are not providing a label. We just have the data. We want to look at it and find the structure. And we're going to use the k-means clustering algorithm that gives us clusters based on what data you passed it. So for the Spark k-means algorithm in a Spark DataFrame, we don't have a predicted label. We only have what are the columns that we're going to use for the prediction. Now remember, k-means can only use numerical data, not categorical or anything like that. So if we had something like the flowers are red and are orange and purple, we have to convert that into a number to be able to include it into the clustering. So let's run the k-means and look at the summary. The summary will give us the coefficient. The coefficients are the centroid of the clusters. Then it will tell us what the size of each of the clusters are. We had 3 clusters. One is 50, the other 39 and 61. It looks like we have some stragglers. And then the last one is the cluster assignment. If you notice there, it didn't tell us what the cluster assignment is because each data point that you passed into the k-means model is assigned a new cluster, meaning if you have 1,000,000 rows, you get a cluster of 1,000,000 rows, right? So it's a Spark data frame with a column named prediction. How do we get that? Well, we could try doing collect. We should not do collect because that's what I was just explaining. It will bring back the prediction for each one of them. So instead, what we really want to do is to see that in the Spark data frame that we had before. And they have included a predict function for the k-means, which seemed kind of odd to me. But what it is doing is to bringing in what cluster number is for each of the data points. Now the original data frame is it has another column called prediction, and that's the cluster number. And again, this is in Spark. It is you do not see it in R. I use display to see that. So as before, let's build a contingency table to see the composition of our clusters. Since we actually have labeled data, we know that the composition is supposed to be very close to what the species are. We see that cluster 0 was assigned, all of the setosas were assigned to cluster 0, but versicolor, most of them, 47 of them were assigned to cluster 2, and most of the virginica were assigned to cluster 1. So we have a mix there. And here we can use ggplot to see the composition of our clusters. Again, cluster 0 is 50 of them are the setosa. Cluster 1 is the virginica, which is the blue. And then versicolor is cluster 2. That's the composition. Okay. So any questions before I go into the extra module? Yes. The unsupervised learning does not have a label. In actual implementations, you don't have a label. You're just telling the algorithm, look at the data, tell me how similar they are, and then cluster them such that the distance between the center of the cluster and everybody else is about the same. And that's how the k-means algorithms work. We have the luxury, I guess, of knowing what the label is for each one of these flowers. Now the question is, did the people that were doing the measurement really classify them well, or is there a way to tell that? We don't know. But it seems like some of the virginica and versicolor are hard to tell apart. So when we were doing the GLM, the previous algorithm that had a training label, we had some errors, and it was basically because the data is really, it's hard to tell them apart. Any other questions? Yes. My understanding is that it will give you an out of memory error. The configuration parameter that we saw at the beginning, it's trying to limit and try to help not make it crash. That's what I'm hoping happens. But it depends on your environment, right? Anyone else?
I imagine these machine learning algorithms are already parallelized implementations. Like how you get some of the numbers at the runtime and what force used.
What was the second part?
How do you get some diagnostic at runtime and how much force used?
So the question was, are the machine learning algorithms running on the Spark data frame already parallelized and are already aware of the Spark data frame structure? And the answer is yes. That's one of the reasons why it has taken a little longer to get implementations in SparkR, because it has to be made aware of all of those details. And to get diagnostics, you will basically use the Spark UI to look at behind the scenes. There is a way to look at what's happening behind the calculations if you are if you want to understand it. And this is the Spark UI again. It tells you what are the stages, what it is doing inside, and how it's working. See a timeline of the events, and also you can look at code that it may be running. So if you are into debugging, that may be a good exercise for you. Okay, good. Now, user-defined functions are one of the things that they have implemented in Spark 2.0. There are 3 user-defined functions, dapply, gapply, and lapply. And in our implementations, they usually mean what kind of structure they are working on. D for data frames, G for group data, and L for lists. So before, we were working with the faithful Spark data frame, and since we unpersisted it, we need to bring it back in. And we were doing the weighting counts. The gapply collect, the gapply and dapply also has a collect method that immediately brings you back the information. So you can put the Spark data frame, the column that you want to group the information by, and then put your function in the call. In this case, we're doing nrow for count. We rename the columns with weighting and count. And this is equivalent to what we had done before with group by and count. So if you run that, it should give you the same information that we had before with a data frame with the weighting counts. Well, let's see. Now, one of the things that if you when you run this again, if you do it with the R data frame versus the Spark data frame, the order that you get your data back from the Spark data frame, it may be out of order. It's not necessarily the same order that you would do it internally. So it's fun to watch, but you have to go back and forth. Still calculating. Because remember, you had to get the data frame, put in the Spark context again, and it's doing all of the grouping and running the function into that. So here, the key is the weighting, which would be the aggregation key, and then X is what else is in the data frame. So we're looking for the number of rows for that key. So as I mentioned before, dapply is applying a function to each partition of a Spark data frame. I do not have an example of that in the tutorial, but if you look at the documentation, good luck. And then dapply collect will bring the information back. And then the other one that I did work with because I was very curious is to see how to apply a function that you have from a library in R. We have a lot of packages that we have from R and that we use. So Spark lapply will allow you to run a function over the list of elements and then distribute that computation into the Spark environment and apply that function in there. The key here will be, we get back to that one. The key here will be that the library that you're using, you have to put it into the function call so that you can get that context into the executors so that they can run that function. Well, okay, let's see, it looks that it's finished. So we have weighting and count. Before we had 70 at the top, now we have 67, it doesn't matter. The point is, it may be reordered because of the way that it is happening in the Spark data frame. It is distributed, it is just collecting, it has no idea of what ordering is. Okay, so let's go back to the Spark lapply. I have to install my package into my R environment. Now I have a list of some large numbers that I want to find the prime factors. And I am going to run prime factors over that list. And the library that I'm using is called numbers. So that's the way to push a library out to the executors, do the calculation, and bring it back. So the first one, for the first number, The prime factors are 3 times 3 times 3607 times 3803 gives you that number. Now, the significance of this example is that my first experience with a distributed computation was at a large national organization that does cryptography, and they wanted to be able to find the prime factors of these very large key numbers. And what we would do is to distribute the computation over the cluster, and each of the cluster will have a piece of a list. Will have a list of prime numbers, and each of the clusters would try to factorize the number, the key that we gave it, with that list, and find out if it was a factor. So I included a link of other resources that you may want to be looking at. There's information about running Spark on AWS, and also more information about data frames versus local R data frames. There are other hosted environments. I have used the IBM Data Scientist Workbench, but that one doesn't run Spark 2.0 yet. So I have used the 1.6 with IBM. And I know that they also have a Spark on Bluemix and the data science experience. Are there any other questions? Yes.
There's methods that are approximate. So what's an approximate count versus just a count?
Oh, yes. So, good question. So one of the things that you get from the summary is the count, and like you said, that there was an approximate count. Because the data is distributed in the environment, they would have to collect all of them and count them, and it may or may not be happen to be the one. So I believe that's why they call it approximate count. So what I think is happening is that they want to do it fast with an approximate count rather than the actual count. If you have a large data set, you may just want to have an idea of what's happening. Okay, there are no other questions. Thank you very much for attending our session, and enjoy the rest of PyData Carolinas. I believe there's some information about lunch.